I will be presenting next on deterioration and degradation of soil biodegradable mulches. I'd like to acknowledge my co-presenters that helped put this slide set together. But let's begin by first defining what degradation and what deterioration are, because I hear them used interchangeably from time to time, and they do have different meanings. So deterioration is a loss of physical or mechanical strength, and it's observed through things like physical testing, microscopic imaging, or macroscopic observations of things like rips, tears, and holes. Degradation, in contrast, is measurable conversion or mineralization of the carbon in that material to carbon dioxide, resulting in a change in chemical structure, physical property, or appearance. Let's see. So the ASTM defines biodegradable plastics as plastics that degrade or biodegrade as a result of the action of naturally occurring microorganisms present in your soil, primarily bacteria and fungi, but possibly also algae. Now, it's important to remember that polyethylene mulch is not biodegradable. The polymers that make up polyethylene mulch have chemical bonds that microorganisms do not have the metabolic pathways to break apart. And biodegradable plastics, as Dr. Mills acknowledged, are made using natural synthetic polymers that have similar bonds that can be broken apart by microorganisms present naturally in soils. So let's spend a little bit more time talking about biodegradation of biodegradable plastic mulches. It is affected by both material properties of the film itself and then the degradation environment. So the material properties include like the chemical and physical attributes and the degradation mechanisms specific for that material. Things such as moisture absorbency and glass transition temperature are essential for that. And glass transition temperature, what that essentially is that the temperature where the film transforms from more of a rigid glassy state more to a flexible state that is more accessible to microorganisms to break it apart through that degradation process. Then the degradation environment is also important. Things such as temperature, moisture, as well as the microorganisms community present will influence biodegradation of biodegradable plastic mulches. Let's revisit the polymers that are used to make biodegradable plastic mulches, or the feedstocks. Dr. Miles provided a really nice introduction. So polylactic acid is one of the biopolymers that are found in biodegradable plastic mulches, or some biodegradable plastic mulches. It's produced from lactic acid produced and fermented from renewable resources such as corn by microorganisms. Now, it has a glass transition temperature close to 60 degrees Celsius or 140 degrees Fahrenheit. What that means is that when it's present in natural ambient conditions such as field soils, it is going to be degrading very slowly because it does not able to achieve that glass transition temperature. However, it is able to degrade in composting temperatures because they're able to reach that glass transition temperature of approximately 140 degrees Fahrenheit or 60 degrees Celsius. Let's contrast polylactic acid, or PLA, to polyhydroxyalkanoates, or PHA. This is a polymer that's fermented from renewable resources such as sugar, also by microorganisms. And it has a glass transition temperature much lower at 5 degrees Celsius or 41 degrees Fahrenheit. And what this means is that this particular feedstock or biopolymer is able to degrade at ambient conditions in the soil. So we're talking about deterioration and degradation. How do you monitor some of these properties? Well, there are a few ways to do this, and we'll spend some time talking about that. So measuring these properties, both physical and chemical, is useful to assess deterioration and degradation throughout the life cycle of that film. And that can range from storage, because biodegradable mulch materials do change in terms of their properties while in a storage environment, even in ideal storage situations. Also, it's able to use in the field to assess mulch functionality, and it can also be used to assess degradation in both soil and composting environments. So physiochemical analyses used to evaluate degradation and deterioration include physical and mechanical things such as tensile strength, elongation at break, weight loss, and thickness. And then examples of chemical ways include Fourier transform, infrared spectrometry, molecular weight analysis, thermal properties, nuclear magnetic resonance, ash content, and radiocarbon analysis. What we're very familiar with here at Washington State University are visual deterioration assessments. These are readily deployed and are very useful to assess mulch functionality. One that we primarily use is a decrease in area or percent soil exposure, and I'll give some examples of that in a minute. You can see some examples too of percent soil exposure due to rip, tears, and holes on these images that I'm showing with my pointer. Photography, Colorimetry, macroscopic evaluations are also useful. And then you can also use more analytical techniques such as scanning electron or laser confocal microscopy. Here on the right here is an image of a scanning electron micrograph of biodegradable plastic mulch with bacteria associated with that film. So I mentioned percent soil exposure as a useful way to assess functionality and deterioration in a field environment. I'm highlighting deterioration measured in one of our experiments. This is in a raspberry field up in northwestern Washington. So you'll see we have percent soil exposure on our y-axis ranging from 0 to 100%. 100% represents a fully deteriorated mulch film, meaning that the biodegradable plastic mulch is no longer really present in our measured area. What we're just able to see is the soil, and it ranges all the way to 0 where that mulch is fully intact. And so you can see from this particular period from May 2017 to April 2018, we have changes in percent soil exposure based on these different materials that we're testing. And in this experiment, we tested 2 EcoBio or BASF biodegradable plastic mulches at 0.5 and 0.6 mil, and 2 Novamont or Matter B feedstock materials that are biodegradable plastic mulches at 0.5 and 0.6 mil as well, and contrasted that to polyethylene mulch. So you can see polyethylene had very little percent soil exposure, which is expected. And then likewise, it was expected that the biodegradable plastic mulches would deteriorate over time. And this is usually a longer period that they're deployed. We're testing these in perennial crops in my program, but we see similar results when we look at annual crops and percent soil exposure in those systems as well. So the degradation process too is something important to consider. So you'll see here, we have kind of the life cycle of the film. It will fragment through the action of just the weathering and brittlement and then tillage in that field soil. And then it transforms and breaks down into microparticles and nanoparticles before it is able for microorganisms to metabolize it and transform it into carbon dioxide and biomass through their metabolism. So you might see the word micro and nanoparticles. Those are kind of buzzwords right now. We're very concerned about micro nanoplastics in our environment. And I do want to confirm that biodegradable plastics do form micro and nanoplastics, but the key thing to remember is the residence time. The residence time for these micro and nanoplastics of biodegradable plastic mulches are shorter, much shorter, and significantly shorter than polyethylene mulch because they are able to then be transformed into CO2 and biomass through biodegradation. So the fate is quite different because they are metabolized by microorganisms, which contrasts to polyethylene, which might be present in undegraded forms or minimally degraded forms for 200, 300 years. Also for reference to what these size dimensions represent, a human hair is approximately the diameter of 100 microns, and then a nanometer is about 1 micron is about 1,000 nanometers, just to give you a scale of reference. And then I'd like to highlight some work also that has come out of Washington State University looking at thermal time and its effect on degradation. And I think this is really shedding some light in terms of how we think about degradation in a field environment. So what this study found is that thermal time or temperature might be a better predictor of in-field degradation than calendar time. So if you remember, we have standards like EN 17033, which has 90% degradation or greater within 24 months at temperatures between 20 and 28 degrees Celsius. And these temperatures might not be achieved in soil environments depending on where you are at, such as northwestern Washington, where we have cool soils. So what this study found is that degree day accumulation was slower in northwestern Washington, which is a measure of thermal time accumulation relative to the conditions in these laboratory tests, such as EN 17033. And so what the modeling data found here is that 90% degradation will take longer than that 24 months period because of our soil conditions and accumulation of thermal temperature, 21 to 58 months. And this would contrast to areas where you have warmer soils. So the other thing I'd like to highlight from this same field study or same field site, but a different paper, is that the mulch films and the biodegradable mulches that were used in this study were degrading over time. So even though we have longer time that it takes to degrade based on this work because of thermal time accumulation, these films are still degrading in the environment, as we can see in this figure here published in another paper. So what we're looking at here is percent mulch recovery. This is from fall 2016 to spring 2020. There were 4 episodes of annual mulch incorporation and tillage starting in 2015, and those are represented by the green arrows. And what we see here, we have several different biodegradable plastic mulch materials. And the key takeaway is that even with annual tillage and incorporation of these biodegradable plastic mulches, the mulch recovery is decreasing over time. In fact, by the end of this study period, only about 10 to 30% remained in terms of visible fragments. So again, what it shows is that the laboratory standards are useful. They don't necessarily mirror what we see in a field environment, and it is highly influenced by thermal temperature or thermal time based on the work previously published, but they are degrading over time as shown in this study. And so I'd like to wrap up my presentation by highlighting some resources. So if you're interested in some of these measurements, such as how to assess deterioration through percent soil exposure, looking at ways to measure plastic fragments in field soils, visible plastic fragments, or monitoring degradation of films, there are these fact sheets and video resources available to you on this website here. And if you are also interested, we do produce a newsletter. You can sign up for that newsletter. It's free. There's about 2 newsletters a year, and you can stay up to date on all the recent information about biodegradable plastic mulches by signing up on this website here and getting access to the newsletter. Okay, and with that, I'd like to point out several other resources for this particular presentation. And then thank you for your attention, and I should have some time for questions.
So we have one question here in the Q&A, and the question is, have you investigated enzymes to increase biodegradation and shorten the time for degradation?
Great question. In fact, Brenda, who was formerly a master's student in my program, co-advised by several of us here, she did look at different compounds to enhance the degradation process in Northwestern Washington. We found that some of these compounds did enhance deterioration, but they didn't enhance degradation in the soil. We're also doing a follow-up study in collaboration with Yasmin and Pam Crone in California and Mark Bolda, where we're looking at some different products to see if they also enhance degradation in soils. But right now, we haven't found anything that rapidly accelerates degradation.